today's topic of discussion is virtual memory. Although I have covered it yesterday, but it was not visible. Let us begin from starting again. Virtual memory. It is a concept which allows user to create programs larger than the actual memory. For instance, if main memory is 1 GB and user program is 2 GB, still this 2 GB program can be made to execute in 1 GB main memory by making use of a virtual memory in the auxiliary memory. There is an area reserved in the auxiliary memory which is known as a virtual memory, which is not a main memory. However, it appears to be part of main memory and enables user to execute programs which are larger than main memory. How the entire process is possible is because of the fact that not the entire program which is stored in main memory is executing at the same time. Parts of the program are executing few parts, whereas few other parts are waiting to be executed and not in execution state. Those which are in execution state, they are kept in main memory, and those which are ready and waiting to be executed are kept in virtual memory. And as the execution proceeds, whenever it is required to bring in the statements, the instructions which are not in main memory but needed for execution are brought in the main memory, and some of the instructions which are not executing in main memory are swapped out of main memory and stored in virtual memory. That is the whole idea of virtual memory. Address space is the set of all addresses used by a programmer, is known as an address space. For instance, if you give names, or friends typically assign pet names, some sort of names to their friends in a group of friends. And having said that, other people outside of the group may not know that those names. If you call each other by using your own given names, that is nothing but the address space of those names, those nicknames which you have been given. And actual names will be your names that appear in your certificates. Those are your actual names. The actual set of addresses of main memory is known as memory space, whereas the address generated by the programmer is known as a virtual address, and set of all those addresses is a address space. And the set of all physical addresses is known as a memory space, and every location in a main memory is having an address which is a physical address assigned for a particular location. So a location will have a physical address, and the set of all such locations is called a memory space. Look at this figure that illustrates the relation between address and memory space in a virtual memory system. Virtual memory is nothing but an area in the auxiliary memory, this part which you see at the left, and the right area here belongs to the main memory. This box is main memory. This main memory stores currently executing instructions and data elements. On the other hand, auxiliary memory stores the instructions and data elements which are not currently executing. The address space is 2 to the power of 20. Okay, 2 to the power of 20. You can use those many locations because of this auxiliary memory or virtual memory actually. The memory space, the size of is 1 to the power of, which is nothing but 32K. This is 1 M, 1 MB to the power of 20. All right. So I hope it is clear. Let me give you another example. Suppose a student has 8 subjects and 8 textbooks are required and 8 notebooks are required. It's totally 16. And his bag can accommodate only 8, 4 text and 4 notebook. He can't put all 16 books in his bag. So what he has to do? He has to put only 4 textbooks and 4 notebooks in a bag which are required for that day. As per the timetable, not all 8 subjects will happen on a given day. What he does is he put 4 text and 4 notebooks in his bag, and he keeps other textbooks and notebooks 4 plus 4 8 somewhere else. That somewhere else is a virtual memory. Maybe probably it is his study table. All right, and his bag is main memory. So main memory stores whatever is required for the current execution, and virtual memory is a large area which stores the segments of program which are not in execution. I hope you all understand this. Memory table for mapping a virtual address. What happens is there is a virtual address. Virtual address is a address generated by the user, and physical address is the address that generated by system. And there is a need to map. You have to map. If I tell you please call X, and it so happens that you call X with his nickname and you forgot his real name, but then you have to you have to have some kind of mapping. X is the real name, nickname is, for instance, A. So you need to map. Given X, you should be able to get A. Given A, you should be able to get X. So like that, here given virtual address, you should be able to map it to the main memory physical address. How it is done? It is done by using memory mapping table. There is a table which stores this mapping, and that memory table buffer register is a register that holds that mapping of memory table buffer. Means, few elements Buffer means, now suppose XA, there are 100 friends in a group. So 100 real names and 100 nicknames. So all that is stored in this mapping table, and one of them which is required is stored in this buffer register, and then that is fed into the main memory address register. This main memory address register gets the 15-bit address from this, and give it to the main memory to get the data the required. If you observe here, virtual address consists of 20 bits, and physical address is 15 bits only, because main memory is smaller than virtual memory. And this way some kind of tables and mapping procedure is used in order to uh, get the real address given the virtual address. Real address is the physical address of the main memory. Okay, what happens here is the table implementation procedure, address mapping using pages. How can address mapping be done using pages? So address mapping uh, can be simplified if it is divided up into groups of fixed size. Physical memory is broken up into groups of equal size called blocks, which may range from 64 to 4096 words each. The term page refers to the group of address space of the same size. This is what is this means. Main memory is divided into fixed size blocks called as pages. And each page can store some words. Okay, and if a page stores 10 words, all the pages will store 10 words only. It is fixed. The page size is fixed. What happens is, user program is also divided into pages. The actual term which is used for main memory is a frame, and for user memory it is page. So what you do is, you take this page and fix into this frame. Like you will have photos of 6 by 4 and 8 by 6 size. When you have a photo of 6 by 4, you need a frame of 6 by 4 only. You can't fix your photo in 8 by 6 frame because the size do not match. Likewise, the user program is divided into equal sized portions called as pages, and main memory is also divided into equal sized uh, segments called frames. And then what you do is, you bring in the user page and store in the frame, main memory frame. So whichever page is required, that is stored in the frame. Whichever page is not required, that is stored in the virtual memory. So that's how this all paragraphs state that only. Look at this. This is address space, this is memory space. What is address space? The set of addresses generated by user is an address space. So there are 7 addresses, actually 8 addresses. They are numbered from 0 to 7. And there are physical addresses which are in this. This is RAM, means main memory. This is main memory. So addresses of main memory is called as memory space, and addresses of virtual memory is called as address space. So addresses 0, 1, 2, 3, 4, 5, 6, 7 is a address space. 0, 1, 2, 3 is a memory space. Okay. So 8K, if considering that each one is having 1K, then you require how many bits? 2 to the power of 13, because 2 to the power of 10 is equal to 1K, and plus 2 to the power of 3 is equal to 8, so 8K. And memory space has only 4 blocks. Frames, I told frames though. Frames can also be called as blocks. So this block and frame is same. So what you do, you put a page in a frame or a block. And this 4K. 4K means 2 to the power of 10 equal to 10. Means 10,024 is equals to 1 KB plus 2 power 2 is equal to 4. So totally 4 KB. So total 12 bits. This is 2 to 2 power 10 plus, you can split up this, 2 power 10 plus 2 power 2. 2 power 10 is 1K, 2 power 2 is 4K. Okay, so that is what this figure illustrates, that these are fixed size units or segments. Memory table in a paged memory. Look at here, this is a page number. There are 8 pages from 0 to 7. These are line numbers. Line numbers means in each page you can have these many number of lines. And this is the reference bit of the presence bit. Presence bit 1 means it is available in the main memory. Presence bit 0 is it is not available in the main memory, rather it's stored in virtual memory. Essentially what happens here is, memory is 4 blocks. Our program is 8 blocks. So you can have only 4 blocks at a time in your main memory. 4 blocks you have to keep some other place. That some other place is virtual memory. And whatever blocks are available in the main memory, for their presence bit will be equal to 1. So a system can determine that these are the pages which have been stored in this memory, and these are the pages which are available in virtual memory. This memory page table, what are you giving in this memory page table? Which one you require? You require 0, 1 and 1. This 0, 1 and 1. So that is given here to main memory address register, this 0, 1. Okay, you get 0, 1, which is page number. This is the line number. So 0, 1 page, what is 0, 1 page number? 0, 1 is this. This is 0, 0, 0, 0. First one is 0, 0. Second one is 0, 1. Third one is 1, 0. Fourth one is 1, 1. So when you want to refer to 0, 1, you are getting to this 0, 1 block, and this line number is here, somewhere here, maybe this line number. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are 10 bits. Alright. What is said earlier is, each page is of size 10 bits. Each page is 1K. 1K means 10 bits. 10 bits means it can store 1024 elements within it. To refer to a particular line, there are 1024 lines. Which line you are actually referring to primarily depends on this line number, which is also known as offset. Okay, associative memory page table. This is another way of to organize the page table. In this, what happens is you have a page number and you have a line number. It will be stored in a register called as argument register. And what is done is this key register and associative. If you recall, associative memory is a content addressable memory, which is the most fastest memory to access. Also, it is the most expensive memory. However, the search is so quick that there is no need to wait. And you know, cache memory, yesterday's lecture, if you listen, cache memory is also implemented in the form of content addressable memory or associative memory, which is like uh, looking for the desired data not by its address, rather by its content. What you are looking for, the same thing you search. So you are looking for 101, page number 101. Page number 101, you want to search. That's why the key register contains 111. 111 is like, uh, it describes that uh, this exact value of this has to be searched here in associative memory. If there is a 1 in key, whatever is available, whatever is the corresponding bit to that 1 will be searched. To this one corresponding is 1, this one is corresponding 0, this one corresponding 1. So because of these three ones, 101 is searched here in associative memory like 101. And because this part of key register is 00, you are not going to search anything at this site. Okay, there is a lecture available on content addressable memory and associative memory. Please go through that if you don't understand. Now there is a question. What is the question? I'll ask you a question. If anyone can know the answer, please let me know. A analogy has been given that if there are 16 books and if students' bag can accommodate only 8 books, he has to put back remaining 8 books somewhere on his study table. Now the question that arises is, next day essentially he can't carry the same set of books because next day timetable may not be exactly similar to the previous day. So now what should be his criteria to change the books in the bag? Can anyone tell me? Yes, please unmute yourself and tell if you know the answer. No? So the criteria here is whichever subjects are not allotted in the timetable for that particular day, those subject books he can take out from his bag, keep on the study table and take those books that are required for that particular day's timetable, keep them in his bag and take the bag to the college. It is like that. It's very simple criteria. What is said here essentially is main memory is smaller than virtual memory. Main memory has only 4 locations, whereas there are 8 pages in the virtual memory. Now, when any one page which is not available in the main memory is required to be loaded in the main memory, which page has to be removed? What should be the criteria? The criteria can be first in, first out, least recently used, random. And if a page is accessed which is not available in the main memory, that condition is called as page fault. When a page fault occurs, program is temporarily suspended and operating system takes the control, brings in the desired page in the main memory, and takes out the page which is not required based on any of the algorithms like FIFO, LRU, and resume the execution of the suspended program. That's how it is made possible that a larger program, larger than main memory, is executed with the help of virtual memory. Memory management hardware. First in, first out means what? What is this criteria? Suppose if you bring in the page at 10 o'clock and at 10:10 you require a new page to be loaded. So the first page which is brought in is at 10. So that you remove 10 page number, page which was brought in at 10. You remove it and bring it the page at 10:10. Next at 10:15 again you require another page, for instance. Then which one you have to remove? After 10 o'clock, suppose at 10:05 another page was brought. So that one is removed. Whichever came in first will go out first. First in, first out. Least recently used, in case the pages are not used for say 2 minutes. In the last 2 minutes that page was not accessed, just remove that page and bring in the new page. That is least recently used, because in the past 2 minutes that page was not at all used and other pages were in use. Memory management hardware, to facilitate this bringing in, taking out virtual memory and all this you know concepts. These concepts can be implemented through hardware and software, both. Operating system should support this in software, as well as specialized hardware is required. What is that specialized hardware? You should have probably the register that stores the mapping of virtual address to physical address, or a register that stores the offset or the line number. Of that sort of hardware is required, and operating system should also support that. Whatever has been covered so far was with respect to fixed size parts or portions of memory and user program known as pages and frames or blocks. There is another way to organize this user program and main memory, that is segmented page mapping, that is segmentation. In segmentation, what happens is the program is not split up into fixed size pages, rather it is split up into the units which are logically coherent, which are having similar instructions or data. Those things are grouped together into one unit, and these units may not have same size. They are known as segments. There is another way to organize the memory, which is segmented page mapping. Segmented page mapping means there are segments which are unequal partitions of memory, and within each segment there are fixed and equal sized partitions known as pages. That is segmented paging. Initially you have a segment. This I can give you an example as you know something, in your bag you may have several compartments. All may not be of equal and fixed size. However, all can be further partitioned into fixed and equal size portions. For instance, if you consider a laptop bag will have uh, several compartments like 4 5. Out of those 4 5, one segment is having sort of cushion and other required belt to place the laptop in a comfortable and safe position. There is another compartment that may not be of same size as this laptop compartment, that can further be divided into small sized partitions. And at the front of the bag also you may have a small a partition which can furthermore be divided into smaller fixed size partitions to store the pens. You can see there are some pens, you know a place where you can pen holders where you can put the pens. So there will be some equal sized four partitions which can hold the pen holders. And then you may find two equal sized portions to hold two smartphones, maybe of size 6 inches. And then you may have a uh, a portion where you can put some long notebooks, 5 long notebooks. Okay, separate compartments. So like that, the same concept you can apply here. Initially you will have segments, they may of be size unequal. Then within each partition you have fixed size pages. Within each page you will have a word is nothing but a data or an instruction. And you have to do mapping to get the block is nothing but a frame in the main memory. So you get a block from this by first getting the segment number and then the page number. When you combine you get the block number and you get the word number. From here you get the word number, and through mapping you get the block number, which gives you physical address essentially. There is an argument register. This is associative memory, translation look aside buffer, which will be useful to speed up the process of uh, looking for or mapping the virtual address to the physical address. And this TLB, translation look aside buffer, is a hardware, a fast hardware that is used to quickly find the uh, address, physical address. So this is hardware support. If you look at this, this is all hardware support. There is a numerical example given. Apparently, this is having segmented paging uh, organization. You have segment of size 4 bits. 4 bits means 2 to the power of 4, 16 segments. You get 16 segments. And 8, 2 to the power 8 is 256. And each page can store 8, 2 to the power of 8 bits words means 256 words. And physical memory is 2 to the power of 20 into 32. And block size 2 to the power of 12 means 2 to the power of 12 is equal to 4096 blocks. 2 to the power of 10 is 1024 plus 2 to the power of 11 is 2048 and 2 to the power of 12 is 4096 blocks, and each block can hold 256 words. This is an example. There are 5 pages, their numbers are given here, and this is segment number 6, and in this you have 5 pages and they are stored in these blocks. These blocks are nothing but the addresses of physical memory, and here it is shown this page table will store the mapping. Page number 35 in segment number 6 is stored in block number 12 here. Page number 36 in segment 6 is stored in block 0. Here, see, here 0. Here also 0. Here it is 12. Here it is 12. Okay, I hope it is clear. Protection is a bit which is used to protect the page. If protection bit is on, some kind of privileges can be given based on the protection values. Full read, full write, read only or execute only, system only. Okay, with this we have completed our unit 4. Tomorrow onwards we will begin unit 5. Please go through today's material. For any doubts, you can contact me tomorrow.